Number 2, the one you guys are doing on your own. Assuming 100 grams of a compound, convert to moles. And anyone have a value for carbon? Anyone throw out? Shout, quick. Value for carbon. 4 point what?
8751.
8751?
Yes.
How about hydrogen? Anyone?
13.6733.
And nitrogen.
1.9557.
Okay, divide each of those by the smallest, which in this case is the 1.9957. Therefore, we get carbon. What's the carbon come out to be? 2.5.
The exact was 2.49.
49. Okay, we'll go with that.
Sorry, I remember.
No, that's all right. And hydrogen ended up being 6.99, and nitrogen obviously ended up being 1, correct? So what are we going to do here? That 0.49 is really close to 0.5, which is 1/2, so double everything, yes? Multiply by 2. So multiply the entire thing by 2, and we get C5H14N2. Everyone concur? Yes.
On AP exam, if we don't write it out first with like 2.49, the 8 points off, can we go ahead and write 2.5?
Yeah, that's fine. I just want to, because if I had gone to 2.45, other people would have,
Okay.
you see where I'm going?
Yeah.
Okay, so anyway, now we also were told that the molar mass in a separate experiment was determined to be around 102 grams per mole. What we want to do is find out if this is both the empirical, which it is the empirical, and molecular formula. So what we have to do is kind of find out the empirical formula mass right away, which happens to be, what, 60, 74, yeah, 30, so we're talking 92, what is it? 102, about 102, right? So it turns out, once again, that the empirical formula mass is the same as the molar mass. Therefore, this is both the empirical and molecular formula. You guys hunky-dory with that?
Wait, say that again.
That is both the empirical and molecular formula, since the empirical formula mass is equivalent to the molecular formula mass. Okay. Sometimes the empirical formula mass is going to be a fraction of that, a whole number fraction of that, to 1/2, 1/3, 1/4, whatever. Okay. And that case is going to give us the multiple that we multiply this by. So anyway, there's that correct answer. We're all hunky-dory on that, right? We've done this like 8,000 times. Here's the thing that not all of you got to experience. So we're going to walk through one of these. Or actually maybe 2 of them. It's called combustion analysis, and the reason they call it that is because that's essentially what was done. So you have a hydrocarbon substance as your sample. Hydrocarbon meaning a true hydrocarbon only has carbon and hydrogen in its formula. But as it turns out, a lot of other organic compounds not only do they have carbon and hydrogen, they might have oxygen, which I think was our first example we did the other day. They might have nitrogen, and they might have sulfur. They might have a number of different other elements. But in general, their base is a carbon and hydrogen compound. What they're going to do is burn the stuff. Now, anytime you burn you don't have to write this down. Anytime you burn a hydrocarbon, what are we reacting it with when we're burning it? You guys all know this. What type of chemical reaction might this be? When you burn something, what are you reacting it with? Oxygen. And what type of chemical reaction is this when we take a hydrocarbon and burn it with oxygen? Combustion reaction. What are the products of a combustion reaction? Carbon dioxide and water. Okay? Now, as it turns out, you might have, let's say, another element over here. Okay? Well, you might get some sort of nitrogen-containing compound also. It's hard to say what you're going to get. You know, who knows? It doesn't really matter. Okay? The point is, there's going to be another compound. We're going to find out. We really don't need to know much about that sometimes. Okay? Because where did all of this carbon end up when we burn it? Into the carbon dioxide. Where did all the hydrogen end up? In the water. If we were somehow, and there's a pretty easy way to do this, able to figure out how much carbon dioxide there was, therefore we would also be able to find out how much carbon ended up there through that percent composition kind of thing. If we knew how much water was formed, we would also know, we could also calculate how much hydrogen was in that, knowing that the only source of those two elements was here. If we knew the mass of this, can you see that we would also be able to find this piece out? Okay. And that's what we're going to use that kind of idea here in a combustion analysis. So, for example, hey, we might get a chance, unlikely, but we might get a chance to make some of this later this year. Substance called ethyl butyrate. It's formed from ethanol. You get what ethanol is, ethyl alcohols and stuff in beer, wine, and all that kind of stuff. And something called butyric acid. Some of you might know what ethanol smells like. They maybe use it in biology as a solvent, possibly. Maybe not. Shoot, I forget where it ended up. I might be able to show you this. I have no idea. Let's see, who did that cabinet? I think Coleman did this cabinet, so it's already. Yeah, maybe. You guys know. It's fun stuff. Anyway, moving on. So anyway, you combine those two things, you get this stuff called ethyl butyrate, which is a chemical that's responsible for the odor of pineapples. Okay? So, anyway, so the ethyl butyrate was combusted, and it's a compound that contains carbon, hydrogen, and oxygen. Okay? And when it was burned, there were 2.78 milligrams of the ethyl butyrate, in abundance, in excess of oxygen, and it produced 6.32 grams carbon dioxide and sorry about that. Yeah, we'll go with grams, my bad. Sorry, the book calls it out as milligrams, we're going to use grams. Make your life easier. You guys okay with that? Okay. And then let's go to 2.58 grams of water. We get rid of that. We don't need that. Okay. So once again, what we need to do is we know that all of the carbon that's in the carbon dioxide originally came from these species over here. All of the hydrogen in the water originally came from here. The oxygen, actually there's two sources of oxygen. All of it showed up over here in one of two different places. Doesn't matter how much, because if we find this out and find that out, then through subtraction we can find out the oxygen. Everyone hunky-dory? So this is basically putting this is where the percent composition data came from the two previous examples that we did. Okay? So we need to find out how much carbon is there. So we're going to take our 6.32 grams of carbon dioxide. I like to cheat a little bit. here. We could do a percent composition thing, but if we were going to do a percent composition calculation for carbon dioxide, we would find out there's one carbon for every one carbon dioxide, right? So we need the mass of just the carbon, which is 12.01 grams. And then the mass of carbon dioxide is 44.01 grams. That's for 1 mole of each of these things. If I were going to calculate the mass percent of carbon and carbon dioxide, that's the relationship I would use. If you think about this, it's almost like a conversion factor. Grams of carbon dioxide cancel, left with grams of carbon. Do you guys agree? Pretty handy-dandy way of doing that. We'll come back and fix that later. We're going to do exactly the same thing for the hydrogen, except this time we're going to use the 2.58 grams of water. If I wanted to find the percent of hydrogen in water, I would take the mass of the hydrogen in the water and divide by the total mass of the water. In this case, since there's 2 hydrogens, it's 2.02 grams for every 18.02 grams of water. Once again, it almost looks like a conversion factor. We can use it as one. And we just need to find out what those actual values are. Has anyone done that yet? Okay, you've got a calculator in hand. Do the carbon, do the hydrogen. Save us a little time. Anybody else can do either one to verify if you want, because occasionally kids make mistakes. Actually, everybody makes mistakes. So we're talking 1/4 of that.
Carbon is 1.72.
Keep going, one more.
All right, 725.
Ah, see, that might make a difference. Okay, that's grams, sorry about that, grams of carbon. And 1/9 of that, we're looking around 0.3-ish.
Yeah,
0.289 grams of hydrogen. Now, that means in this, 1.725 grams of it is carbon and 0.289 grams of it is hydrogen. How much of it is oxygen? Well, we would take the total, right? I use the abbreviation CMPD for compound all the time. You'll see it elsewhere, so go ahead and get used to it. We're going to subtract from that the mass of the carbon and the mass of the hydrogen. You can do it all in one shot if you want. I don't know what that comes out to be. Someone wouldn't mind filling
Why do you
that.
have force figures for the carbon?
It doesn't matter. It doesn't matter. We're going to an empirical formula. We're going to go down to 1 anyway. So I like to carry as many extra along as I can for a while with these. Anyone have a result for the oxygen?
0.776.
0.776.
Or 766.
766 grams of oxygen. There, that is the mass of each of the elements that is represented in that 2.78 grams of compound. If we want to find the empirical formula, what do we do next? We forgot a step. We don't have to find a percent. We could. Because then that would give it, but remember what we did is assumed 100, we were given a percentages, so we assumed 100 grams of compound because we didn't have anything else to go on. But once we assume that 100 grams, now we've got masses. What do we have right now? Masses. That's what Lauren did. You skipped a step, convert to moles, then divide by the smallest. And see, that's, if you're going to make a mistake on this, it's that convert to moles piece. Okay? Chemistry, all about the mole. So, convert to moles, divide by the smallest. Ready, set, go, if you haven't already started. And you know what to do from here because you've done that. Here's the deal. I will not be here tomorrow.